then as well. But what I'm really going to try and explain is something that we were trying to understand for a while, is something about the relationship between cluster algebras and discrete integrability. So in case you don't know what a cluster algebra is, don't worry, because I'll try and give you a very, very rapid definition. I've got my work cut out because normally you need a whole hour just to define it, but I'll do my best. But in short, a cluster algebra, you could say, is some kind of combinatorial structure which appears in certain relations, algebraic relations between special coordinate systems, in particular algebraic varieties. So that's in a mathematical context. For example, if you consider Grassmannians, or you consider Penner coordinates in Teichmuller theory. But there are also many examples in theoretical physics, such as Y systems, T systems, Q systems, which are functional relations typically between pseudo-energies or Boltzmann weights. So whether if you're doing solvable quantum field theory or solvable lattice models of statistical mechanics. So that's the sort of context where a lot of these things appear, and they were introduced, cluster algebras were introduced by Fomin and Zelevinsky in around 2000, essentially to give an explanation, a sort of a unified explanation for some of these phenomena that appeared in these widely varying contexts. But also cluster algebra structure was also noticed in discrete integrable systems. So in particular, in discrete integrable systems, if you look at discrete Hirota equations, then you see an example of a cluster algebra structure. So bilinear equations for tau functions have discrete bilinear equations have this structure. I don't want to try and explain the general situation in lattice equations, because that's too difficult. You need an infinite cluster algebra. But really, what I'm going to explain, and what I'm going to explain today, is all about finite dimensional systems. So, and it's typified by this example. So this is going to be my running example for the next 20 minutes or so. So this is called, this is known as the Somos 5 recurrence. And this is a bilinear equation, but it's an ordinary difference equation. So this is actually a reduction of discrete Hirota equation. And one of the phenomena which is associated with cluster algebras, you can see if you set the initial values of this recurrence. So we take, say, x0, x1, x2, x3, x4, and set them all to be 1. And so you can start iterating, and if I don't make any mistakes, I think you can check quite quickly that those are the first 5 terms you generate after the initial 5 ones. And then at the next step, something interesting happens, because in order to generate those 5 numbers, we had to divide by 1 5 times in order to solve this relation for xn plus 5. So there's no mystery that those are integers. But when we do the next one, we have to do 3 times 37 plus 5 times 11, and that's a sum of 2 odd numbers, and so we can divide by 2. So I think we get 83. And then the next stage, you can do it again, and you'll find that when you multiply the 2 numbers and add them, you get a multiple of 3, and I think you get 274, and it goes on happening. I think the next one is 1,217. And as far as your eye can see, or your computer can see, you can see integers. And the explanation for this, so this is just with integer values as a starting point. But the explanation for this is that this recurrence has what's called the Laurent property. So the Laurent property in this case says that if you consider, so I mean you know that the iterates are going to be rational functions of the 5 initial values, but what's surprising is that they're actually Laurent polynomials in the initial values with integer coefficients. So they belong to this ring of Laurent polynomials. Okay, so they're polynomials in those values with integer coefficients, and if you just substitute all the initial values to be 1, it's clear that you're going to get an integer sequence. Okay, so that's and this property is a property which is generated by the axiomatic structure of a cluster algebra. So the types of systems that I'm going to just tell you about that we studied with Alan starting here a few years ago is a family of recurrences of the similar structure to this, but we can think about an arbitrary order n so we call these things cluster maps. You can think of them as nth order recurrence relations, where you have a product of 2 terms on the left and then a sum of 2 monomials on the right. So I'm going to write them like this. This may seem like a perverse way to write things, but it's sort of convenient. So you have, this is defined by an n-1 tuple of integers. So A going A1 up to AN-1, and it has to be palindromic. So what I mean is that AJ is equal to AN minus J. So this sequence is a palindrome. So we pick any n-1 palindrome, and some of those things will be 0. They're not going to make any can be 0. They don't make any contribution. Some of them are positive, and some of them are negative, and we just partition them into the positives and negatives, and then we can write down the recurrence of this form. So all the recurrences of this type can be generated by a sequence of mutations, what's called mutations, in a cluster algebra, and this was work of Fordy and Marsh, who classified recurrence relations which could be generated by cluster algebras. So, in order to see how that works, let me now explain what I mean by mutations and sort of what I mean by cluster algebra. So I'm going to talk about the simplest kind of situation, what's called often geometric type cluster algebras, and they can be constructed from quivers. Okay. So a quiver is just, you can think of a bunch of nodes and a load of arrows between them, and we take in this case we think about quivers Q, which don't have any one cycle, so you can never have an arrow going from a node to itself, and also you can't have 2 cycles, so you can't have, say, an arrow going from between one node in one direction and another arrow going in the opposite direction. So without 1 or 2 cycles. And such such quivers, it's easy to see, can be encoded in skew-symmetric integer matrices. So if we take a quiver with n nodes, then we can take a skew-symmetric matrix so you just, if there's an, well, I think the convention we normally use, if there's an arrow going from node j to node I, then that counts for 1 in bij, and if it's the arrows going the opposite way, it counts for -1. So you can see how that works. And well, so as an example, our main example here, I can tell you what the quiver looks like. So actually, it's easier for me to go in the opposite direction. So if I start from a 5 by 5 skew matrix, and essentially the top row of the matrix has got to be the n-tuple, n-1 tuple that I mentioned. So here we've got sort of, there's a 1, 1, and there's a -1, -1 in the middle. So that's the n-1 tuple that corresponds to that SOMOS 5 recurrence over there. And oops, no, I can't move it up. Well, it's got to be skew, so we know what that looks like. And it has various other symmetries. If you want, if this matrix has certain symmetries, if you want it to generate cluster mutations in the correct way. So in this case, I just calculated it earlier today. So the matrix looks like that, and then 1, 1. Okay, so hopefully you can read that all right. And then what does that look like as a quiver? Well, in this case, if we draw our 5 points, label them 1, 2, 3, 4, 5, then with a choice of sign convention, we'll have an arrow going from 2 to 1 in that way, an arrow going from 5 to 1. We'll have arrows going out, 2, 3, and 4, like that. And then if we look at the second row, we've got to have 2 arrows going like that. And we've also got to have 1 arrow going out like that. And if we look at the third row, we've got to have 2 arrows going like that. And if we look at the, is that everything? No, there's also something else. We've also got to have an arrow like that. And finally, in the fourth row, we've got to have an arrow there. So hopefully, yeah, maybe I'll just redraw that slightly to make it clearer. Okay, so hopefully you agree with my assignment of arrows to numbers. And now I want to tell you then how do we generate recurrences from this setup. So our data consists of the quiver, or equivalently the skew integer matrix, and then we start with also what's called a cluster, which now is an n-tuple of variables. So I can label it x0 up to x minus 1, or x1 up to xn is more commonly used in cluster algebras. And that's going to be like the initial data for my recurrence. Okay, and so now let me describe how it works. Well, I can get rid of this, or no, maybe I'll do this. So what we want to do is quiver mutation. So quiver mutation is easy to remember how it works. So just given this matrix B, we have a quiver, and given a quiver equivalently, we have the matrix B. So I'm going to describe the quiver mutation, and then what's the equivalent, what's called matrix mutation. So depending on whether you prefer pictures or algebra, which you can remember either of them. So we have n nodes in our diagram, capital N nodes in our diagram, and we can choose to mutate at any one of those nodes. So the mutation mu k at node k, how does that work? Well, we reverse all the arrows that go in or out of node k. Then if we have between I and k, if we have p arrows going from I to k, so I guess I should say if we have p arrows going from I to k, and if we also have q arrows going from k to j, then we should add p times q arrows going from I to j. So p times q arrows should be added between those two nodes. And then finally, we need to remove or cancel out any two cycles that might be created in the second step. Okay, and in terms of algebra, you can check that that means that, so this will produce a new quiver from the quiver Q that you start from. So Q gets sent to, let's say, Q prime, which is the mutation M mu k acting on Q. And here we have the matrix B with entries Bij, and the rule is that well, B gets sent to mu k of B, which I can call B prime, and the rule is that the entries of the new matrix have the signs reversed if I equals k or j equals k, and otherwise we take Bij plus and then a slightly complicated looking formula, but it's not really very complicated. It's just encoding the second and third rules here. Okay, so it's not too hard to check that those things are equivalent, whether you want to operate with formulae on matrices or you want to operate with pictures. But there's something special about the quiver that I've written down, and I told you that I was sort of doing some calculation to obtain that matrix starting from the first row. So the point is, let's rub that out, because I'm going to just operate with the picture. So maybe, because my time is short, I'll cut to the chase and just sort of show you the answer rather than doing it, but it's a good exercise if you've never done this to try it on this picture. So if we pick, in particular, let's pick the first node, mu1, and apply it to this quiver, then what I claim is that the answer is just going to look like the same quiver, but with a cyclic permutation of the nodes. So let me see, what do we want there? We want those two going like that, and we want those two going. So this is if this is Q, then where we started with, then this is what you get from doing mu1 of Q, and with this labeling of the nodes, you can see that it's just equivalent to a cyclic permutation. So what Fortier-Marsh did I don't know, I forget the exact year, but 2011, is that right, Alan? Or so yeah, okay, so 2011. They classified all quivers Q which are periodic under mutation. With period 1. So what period 1 means is that you do one mutation at some particular choice of node, and that's exactly equivalent to the cyclic permutation. 1 goes to 2, goes to 3, and so on. You can consider more general periodicity, and they and others, and Nakanishi have looked at more general periodicity, and it's a difficult problem to classify quivers with periodicity. But why were they interested in this? They were interested in it because in addition to the matrix mutation or quiver mutation, those equivalent things which act just on the level of these matrix entries, let's say, there's also some what's called cluster mutation. So cluster mutation so we start with our initial cluster X, and then under mutation at mu k, X gets sent to, let's say, mu k of X, which I'll call X prime to be consistent with my other notation, where, well, the cluster mutation is quite simple. So xi prime is equal to xi if I is not equal to k, and then to find xk prime we use the what's called the exchange relation, and that's exactly, let's write it this way. And what you can see in this formula is that the elements in the kth row of the matrix or the kth column, depending on what my convention is, will, depending on what your convention is, they appear as the exponents. So the situation that we had here, we had a set of exponents on the first row, and we chose to do mutation mu1 on the first node. And so the exponents were exactly the exponents 1, -1, -1, 1 that give you the Somos 5 recurrence. So that means that when you do the mutation mu1, you get x1 prime times x1 is x2 times x4 plus x, I got it the wrong way around. Yes, x1 times x4 plus, what's my, sorry, x1 times x1 prime is equal to x2 times x5 in this case, because n equals 5, plus x2 times x3. Yeah, I think that's right. I hope I said it right. So let me write it down just so I don't confuse myself anymore. If you do Somos 5, then x1 prime times x1 has got to be x2 times x5 plus x3 times x4. Okay, so that's just one mutation. But the point is that if we now look at the quiver that we get from doing mu1, then it looks exactly the same as the quiver we started with up to this cyclic permutation. So now if we do mutation mu2, then the exponents that appear in the exchange relation are exactly the same as they were the first time. So for a general matrix B or a general quiver, you're going to get a different recurrence, a different formula, at each step of mutation. And in general, a cluster algebra doesn't generate a single map. It generates a tree of iterates from each initial cluster. So Fordy and Marsh were interested in classifying this periodicity because they wanted to see when can you generate a single dynamical system from cluster mutation. So that's the motivation. So that's enough of the introduction of the talk, and now let me just quickly summarize the results of our study in a couple of minutes. So what are the properties of these maps which are generated by recursively applying these mutations, mu1, mu2, mu3, when you have a cyclic quiver? So the maps you generate, you can think of them as just they're birational maps in n-dimensional space, and they are given by this recurrence formula. And they have a symplectic structure, or more generally a presymplectic structure, which is given by the element, essentially it's constant in the log coordinates. And so we can ask ourselves, can these maps be integrable? So it turns out that if you want to classify the integrable cases, it's enough to look at the entropy. Well, that's a good indication of integrability. And because of the Laurent property, then you can measure the degree growth by the degrees of the monomial denominators of these Laurent polynomials. Oops. And the exponents so the exponents satisfy the tropical version of the map, which is the following. So I mean the max plus version of okay, I'm really finished now, Chris. So if you want to understand, if you want to find out whether these things are integrable, you look at their tropical versions, and that allows you to calculate the entropy. And then what you finally arrive at is there are only 4 families of maps within this very large class which are integrable. But of course, entropy doesn't prove integrability in the Liouville-Arnold sense. So then you have to, by hand, construct first integrals and so on. So that's what we did with Alan. Thanks for listening.
I think we have time for a few questions.
Any non-autonomous version is available?
Yeah, that's something that's sort of ongoing work, which I've started doing with Inoue and Nakanishi. So what I told you about was what are called coefficient-free cluster algebras, but you can put coefficients in, and there's a dynamics on the coefficients, and they generate essentially Y systems. And it turns out that within Y systems, you can find non-autonomous. So, for example, you can get Q-Painlevé equations from Y systems. So, in the preprint version of our paper with Alan, the long version on the archive, you can see an example of that. But the published version, the short version, we had to take out a lot of stuff. So, that's, yeah.
Could you somehow characterize these 4 families?
Yes, certainly. So, the 4 families so family number 1 is purely periodic orbits. I mean, all orbits are periodic. In fact, it just corresponds to copies of the famous Linnaeus 5 cycle. So it's really the S5 cycle. The families 2 and 3, which are associated with linear growth of degrees, they're linearizable maps. So these were considered first by Fordy and Marsh, and then some examples I considered earlier, and then Keller and Shorotska proved some general things about linear relations in cluster algebras, which are generated from affine Dynkin quivers. So case 2 actually corresponds to affine A-type quivers. Case 3 seems to be something new, and we don't exactly know what it is, but it looks more sort of Boussinesque type, or reduction of Boussinesque. But these ones are actually a reduction of the Poisson structure. It actually gives you the Poisson structure of the dressing chain. So these ones are somehow related to KdV, although the dynamics in the cluster variables is linearizable. And the last one is the Somos type, like the Somos 5, and those are associated with reductions of discrete Hirota, and they have algebro-geometric integrability in the sense that the level sets will correspond to Jacobians of algebraic curves. So they're sort of like algebro's geometric solutions of discrete Hirota, basically. So that's the classification. Yeah. Good that you asked the questions.
I think we should finish.
Yeah.
Okay. Thank you, our speaker.